Okay, let's begin. I don't really pay attention to averages. I know a lot of people like doing that. I was never really
Well, range probably.
Third highest score and fourth lowest.
It's more of a personality thing. It's kind of like, when I was a kid, I would tell my dad, well, I didn't do so bad on this test, but I did better than most people. He's like, I don't care about other people. You are supposed to be here. I don't care about what anyone else does. So I stopped caring about averages ever since I was a little kid. Like, I don't care how anyone else does. You worry about you. I don't grade on the average. Okay, so last time we looked at some more techniques for solving higher order differential equations. It's kind of out of it last time. I don't even know if anything I said made sense, I guess. I'm hoping. I think the only people who followed was the people who actually studied up on their own. But let's see what sunk in. How do we do this?
Characteristic, r cubed plus 5.
How would you deal with that?
I cubed equals negative the roots.
5. Then?
That's -1.
That's identity.
R cubed is equal to 5 times -1. And if I think of R cubed as a polar form of a complex number, I'll say R e to the I theta. And I think of -1 as e to the I. What does that mean?
Pi plus 2 pi n.
I plus 2 and pi. And of course, n goes from 0 to 1 less than the power. Basically what this would mean is if I were to solve for r e to the I theta, I would get the cube root of 5 e to the I 2 n plus 1 pi over 3. So even if you don't remember the sum of cubes formula, which you could actually technically use it here, just write that as the cube root of 5 cubed, use the sum of cubes formula. This way is still going to get you all the answers you actually need.
It also sucks doing it that way to check
Which way?
the sum of cubes.
Oh, you actually checked it both ways?
Yeah,
Yeah.
not good.
Yeah, because you'd have like quadratic formula with like
Yeah.
1/3 all over the place. Yeah, it's not gonna be pretty. But here, assuming your trig is up to scratch, this way probably won't be so bad. So what you would do is, of course, for n equals 0, your r is going to be equal to cube root of 5 times, so you're going to plug in n equals 0, you're just going to get pi over 3, e to the I pi over 3 is cosine of pi over 3 plus I sine of pi over 3. Cosine of pi over 3. Sine of pi over 3 is over 2. Plug in n equals 1. Then we would have our r would equals to the cube root of 5, e to the 3 pi over 3, which is just e to the I pi. We know that's -1. And n equals 2.
That's just a complement, right?
Huh?
That's just a negative sign.
Right.
over there.
I am not going to have to go through this again because I know complex roots come in conjugate pairs. So if there's one with a plus here, there's going to be one with a minus. So those are the roots. This means our R1 is equal to minus the cube root of 5. Our R2 of 3 is going to be equal to the cube root of 5 times 1/2 plus or minus I. What does this mean for our solution, which is the homogeneous solution?
C1 e to the negative square root of cube root of e to the cube root of 5 cos half over 2 cosine square root 3 over 2.
Well, cosine of the cube root of 5 square root of 3 over 2. T. Right, because I'm multiplying these up.
Oh, yeah.
Plus C3 e to the cube root of 5 t over 2 sine of the cube root of 5 cube root of 3 over 2t. And yeah, you can just imagine what using the formula, the quadratic formula.
75% through, and I was like, this
Yeah,
is
you just gave up, yeah. So it's a nice method, this method called roots of unity. Okay, so any questions about that one? Anywhere we're not sure what happened?
When we have the complex number, you can go first.
Yeah.
What happened to the e to the I pi from n equals 1?
Oh, e to the I pi is minus 1. That's something we knew. That's from the main equation. That's the most important one. This is cosine pi plus I is sine pi. Sine of pi is 0. Cosine of pi is minus 1. So that's where that negative sign came from.
When we're doing for the complex roots, I know you were defining it via an angle and how long the vector stretches. That's just a regular real number plane on the x-axis, right?
The real number line is the horizontal axis, yes. And the vertical is
The I-axis, right?
the I-axis, the imaginary axis, right. So a coordinate in that plane is representing a complex number. The first coordinate represents the real part, the second coordinate represents the imaginary part. And you're just really defining the coordinate, that makes it work. Other questions? Let's do this one. So, characteristic is this. So you get that. Imagine this to be the polar form of a complex number, and that minus 1 I can write as e to the I again to n plus 1 pi over 2. Pi. So this means that this guy, which is just me rewriting r, my r is going to be the fourth root of both sides. It's going to be e to the I 2n plus 1 pi over 4. And n goes from 0, 1, 2, 3. We stop it at 1 less than the degree because after that it just starts to repeat. And yeah, now you plug in n equals 0. This means r is equal to e to the I pi over 4, which is cosine pi over 4 plus I sine pi over 4. We know that this is radical 2 over 2 plus I radical 2 over 2. And n equals 1. Plug in 1 over there, and I get 3 pi over 4. So my r would be e to the I 3 pi over 4. That's just cosine of 3 pi over 4 plus I sine of 3 pi over 4. That's going to be minus radical 2 over 2 plus I radical 2 over 2. And I already know the other side. So this is my, say, R2. That is my R1. And my R3, I don't even know if this is the particular order, but it doesn't matter. It's going to have a minus for that one, and then R4 is going to have a minus for the other one. so, finally, we have our y is equal to C1 e to the
2 over 2.
radical 2 over 2t cosine radical 2 over 2t plus C2 e to the radical 2 over 2t sine radical 2 over 2t plus C3 e to the minus radical 2 over 2t cosine radical 2 over 2t plus C4 e to the minus radical 2 over 2t sine radical 2 over 2t. That's that answer. And again, once you do a few of these, you should be getting the hang of it. Getting bored pretty quickly. Let's actually get through the last one. So now let's do the non-homogeneous case. What's the first thing to do in the non-homogeneous case?
Find the particular.
You still find
Homogeneous.
first find the homogeneous, because when we choose the particular, it should not overlap with the homogeneous. So we're first going to do that. And
Did we already solve that?
I feel like we solved this last time, right? Anyway, this one is probably easy enough to do that. So my r
Should
is
be
equal to
r squared minus r?
plus minus. So r is equal to minus 1, or r is equal to minus b plus minus the square root of b squared minus 4ac all over 2a. It's going to be 1/2 plus or minus radical 3 over 2i. So this means my homogeneous solution, twice of h, is going to be c1 e to the minus t plus c2 e to the t over 2 cosine radical 3 over 2t plus c3 e to the t over 2 sine radical 3 over 2t. Now, suppose we want to do undetermined coefficients. What would you guess the particular would look like?
AT plus B plus C.
Come again? AT plus B?
Plus C e to the negative.
Because we have a first order polynomial there, so we write down the general first order polynomial, and then I check, is that overlapping with anything here? Nope, there are no polynomials there. And then
C e to the negative.
C e to the minus t.
It overlaps. First
Now we notice that overlaps here, so I'm going to multiply by t. That would be my particular solution. Now I want to find a, b, and c. How do I do that?
differentiate it twice. Oh yeah, thrice.
What?
Differentiate it thrice.
Thrice. Yes. So differentiate the t, leave the e to the minus t, plus leave the t, differentiate the e to the minus t.
Put a prime.
This is a prime, which I can write as a plus c e to the minus t times 1 minus t. Then I can find the second derivative. Differentiate a, it goes away. Differentiate that one, minus c e to the minus t times 1 minus t plus minus c e to the minus t. This is equal to minus c e to the minus t. This would be 2 minus t, right?
Nice.
By p to the prime. C e to the minus t times 2 minus t.
Huh? This look? R cubed.
Come again?
Negative.
Oh,
Oh, no, no, no.
Yeah, it's just a negative C and a negative T. You just copied it down wrong.
Yeah, you got the negative minus C.
What do you mean?
Left.
Just here?
Yeah,
This, the negative.
there's a negative in front of the C.
No.
I'm differentiating.
Yeah. Yeah, that's right.
Oh, I thought.
So I differentiated e to the minus t
Oh,
and left this, then I'm going to get that, which is going to be a c e to the minus t, 3 minus t. Right? Now you plug it into the original. So I'm going to have the c e to the minus t times 3 minus t plus the original y, at plus b plus c t e to the minus t. That will equal to t plus e to the minus t. And this here is my y triple prime. This here is my y. So y triple prime plus y equals this, and now I will group like terms. So we have the at plus b. Let's look at the e to the minus t's. So I have 3c e to the minus t. Takes care of that. And that's that, right? And then if I look at the t e to the minus t, I would have minus c t,
Would that be 0?
and I have plus c. So this part is just going away. Okay, so now what?
A match, B is 0, C is
A equals 1, B equals 0,
C
and I have
3c equals
3c equals 1, which means that c equals a third. Which means that my general solution, black guy, plus
T.
t, and the 0 plus 1/3 t to the minus t.
Should be 1/3 e to the minus t?
1/3.
Oh, it should be just negative 2.
No, the original is a t plus b plus c t e to the minus t. Right, so this here
Yeah.
is my yh, and this here is my yp, and that is the general solution.
Can you remind me why we have more terms than we have derivatives? I think we've been just tired, but I was thinking that I needed to have 3 terms coming out of this. Is it because there's a particular?
There are 3 linearly independent solutions for the homogeneous case. This is a particular case. Kind of the best visualization I can give you, it's kind of like these guys are the vectors that create the space, and then this is a point that allows me to
In that space.
create that plane in that space. Right, just like when you have you want to create a tangent plane, you need a direction and you need a point. Think of this as the point. That's where we ground ourselves. And okay, from that we can expand in these directions to create all possible solution spaces.
Makes sense.
So it's kind of a linear algebra visualization thing. Okay, and that's that. So, yeah. Now, of course, for this, you have to remember how to actually factor polynomials using all the techniques I talked about. The roots of unity is going to be new. You probably haven't seen that before, but other than that, pretty much everything I talked about was in pre-calc. And if you forgot anything, like your trigonometry, how to factor, how to divide things, which I don't want to waste any more time going into, you can actually go watch my pre-calc videos. And just
Do you
start
know
there.
where we can find practice problems for roots of unity? I don't think they're in our book.
Well, you can make them up. Yeah. Y to the fifth plus 9y equals 0. That's a roots of unity problem, right? Once you have the highest power and only the y term, that's a roots of unity problem, right? Once you throw in something else, plus y triple prime, now it's not a roots of unity problem anymore, right? So pretty much your roots of unity problem happens when you have two terms. Yeah, pretty much when you have two terms on one side is when you get a roots of unity problem. If you don't have the y, it can still work. So you might have y to the 7th plus 3y triple prime equals 0. What I could do is just do a substitution, u equals y triple prime. And so this would be u to the 4th derivative plus 3u equals 0. That's the roots of unity problem.
But you have to have two terms.
So it has to be two terms, right? You have like one thing moving on the other side, and you're just taking the root. Yeah. So you can pretty much make up a problem,
Right.
solve it by hand, and check it with Wolfram alpha or something like that. Right. You can just have Wolfram alpha factor x to the 7th plus x cubed plus 3x cubed. Tell me find all the roots. It'll find all of them, and you just check. Did I get all of them? You know? So it's easy to actually make up your own problems and challenge yourself. So that's when you get bored and you're like, man, the problems in the book are too nice. It's too easy, man. Let me give myself a challenge. And you start making up your own problems.
I have a question.
Yes.
What does it mean for it to be like a complex root as opposed to a real root? Like
It has an I attachment to it.
Like, what does that mean, like geometrically? Like, is this in the complex
It
plane?
exists in the complex plane.
If you're thinking of all the numbers in the complex plane, the real ones are the guys that lie along the axis, the horizontal axis. Once you leave the axis, you now have an I term. We call it a complex root. The real guys are the guys that live along this line.
So any point not on the horizontal axis is a complex root.
Yes.
Well, the ones
That's
on the
how-
horizontal axis are complex too. They just have.
Yeah, we
zero.
tend not to think of it though because it's a plus 0i. And we just tend to think of that it's a regular real number.
Does it
In
mean
some
all real
sense.
numbers or complex numbers?
Yes, you can think of it that way. And usually you won't get in trouble for that until you go to a class like abstract algebra, because there are ways in which the complex plane and the real numbers don't gel well together. But for us, you can actually do that. Okay, now I actually want to move on to a completely different thing, which I wanted to start last time actually. We're going to move on to chapter 5, where we're going to talk about everyone's favorite thing, series solutions. I believe we're still sticking with, no, we're not even going to stick with constant coefficients anymore. We're actually graduating from that. Because series can make things a lot nicer. You don't have to worry about all the worries here.
Oh my god.
So, let's focus on second order linear differential equations for now. Okay. So, given, say p of x, y prime plus q of x, y prime plus r of x, y equals 0. We could have something over here, but let's deal with the homogeneous case first. I'm going to give you a definition. The set of x's, let me write it if x naught such that p of x naught equals 0 is called a singular point. Now, singular like the singularity where the Big Bang happened, stuff blows up. Why? Is because if we were to put this in standard form, we would divide through by p. And notice that we would lose continuity in that case if we divide by p. So where the first coefficient equals 0 is going to be an important thing for us to consider. We call this a singular point. We're not going to deal with those right now. We'll deal with those in like 5.0, 5.4, something like that. Otherwise,
The series solution would work for specifically second order.
no, it works in general, but I'm going to show you using second order because, as you will see, these problems can get quite long, and I don't want to have to go beyond second order. Okay. Otherwise, x naught is called an ordinary point.
It's like a double negative.
Huh? What?
I thought you
Thought I said what?
said not. I thought you said x naught is called an ordinary knot.
Oh. X naught.
And then I said double fisherman.
Yeah. First, focus on solving an ODE with series at an ordinary point. I will show you how you will deal with singular points later, but let's actually look at an ordinary. Here is what we are going to do. The idea is the following. Back in Calc 2 or Calc 3 for some of you, we learned the idea of something called a power series. So sometimes you have these functions that behave very nicely. For example, they were infinitely differentiable. And you could create what's called a power series from them, or a Taylor polynomial. And sometimes those Taylor polynomials will actually converge to a function on some interval. And we can actually use the power series in place of the function, which is very convenient. So what we are going to do is pretty much the same thing. We're going to set y equal to some power series. It goes from 0 to infinity of a(n) x minus x naught to the n. Okay? So this is i.e. assume we can find a power series for y. Centered at the ordinary point. It's not. No. Let's review series a bit. Because I can, because from here on now, it's going to get very sketchy if you don't remember some series stuff. So, let's talk about that.
Are we gonna have to remember all the tests?
No, you won't need to know the series tests.
Nice.
What you are going to need to know is well, you should, but I'm not going to test you on it. What you are going to need to know, though, is how to do arithmetic with series, how series will function algebraically and arithmetically.
Yeah, that's right.
What? But I hope that's for you. Okay, but what is a series? First of all, a sequence, which we might call an, is a function from the natural numbers to r, let's say, we're looking for real. that is 1. Another way you can look at this, a sequence AN is a list of numbers in a definite order. So you can think of, if I list a n, you can think of this as described, these are squiggly brackets for a set. You can think of this as just a list where our n is in n. So you have A0, A1, A2. It's just a list of things in a certain order where we're starting from n, which I might write as equals 0 to infinity. And this says it's an infinite sequence, which usually is the one we're going to care about. We're not really going to care about a finite sequence. So this means it literally goes on forever. You start at 0 and you keep going forever, and you get an infinite number, infinite list of numbers. You can also have a finite sequence, in which case you can start at 0 and then you say you go up to some finite integer k. So this is a finite sequence. So it terminates. So it's like you start at A0, and it's series number A1, A2, and the list continues until you get to AK, and then it stops. So you can have a list of numbers in a definite order. Now, Now the AN just describes a function. A0 is just the output when you plug in 0, A1 is the output when you plug in 1, A2 is the output when you plug in 2, etc. Now what a series is the sum of the terms of a sequence. And the notation is the following. We write uppercase sigma. And then we can write something like this, up to infinity. This is the example of an infinite sequence. And we write a n. Now, this basically means you start at 0, you plug in 0 into whatever that formula says, and then you add that to when you plug in 1, add that to when you plug in 2, add that to when you plug in 3, and this continues ad infinitum.
Professor,
Yes?
are we ever doing multiplication of series? The two i's one?
No. But we do need to know how to add and subtract. You would need multiplication of series if you had nonlinear, right? If you have two y's multiplying by each other, then that's when you get multiplication of series. That is way more annoying. This thing here is called an index. Plural indices. This here is the starting point. Okay? Or lower limit. This here is the ending point, or upper limit. Now if you write infinity, it means there is no upper limit. Infinity means no limit. You just keep going, right? And you're adding up the terms of the sequence. And we know from Cal 2 or Cal 3 that every now and then you have a series where this adds up to a finite number. You can add an infinite number of things, and you can get a finite number, which to some people is very strange, but if you, I guess, think about it abstractly, it actually makes total sense. One of the first illustrations of these came like, I don't remember, it's one of the BCs, 300 BC, 500 BC.
Is it the arrow, which is like is shot
The arrow thing, yes, which is, what's that guy's name again? I always
It's
forget.
Zeno's paradox?
Zeno, yes, Zeno. So when you kind of think of someone is 10 feet from a target and they shoot an arrow at the target, it turns out that you can abstractly dissect this in your mind as the arrow has to cover half the distance between it and the target, and then eventually cover half of that distance, and eventually cover half of that distance. And so you can think of the arrow as covering a list of numbers, right? Where the total distance the arrow travels is just going to be the sum of these numbers, and then you're like, well, if I'm always taking half the distance, would I ever get to the target? And we know in reality, it does hit the target. So there must be a way to add up an infinite list of numbers and get a finite number. So that is what, when things really get interesting, when our series adds up to a finite number, we say the series converges if it adds up to a finite number. We also have the appreciation that in this case, we have, here's how you think about what it means to add up an infinite number of things and achieve a finite number. You talk about what's called the limit of partial sums. So basically, you add up the first n terms, big N terms, and then you carefully extend that list going off to infinity, and eventually it will hit a number which we can call it. And if that number is finite, we say the series converges. And in Calc 3, a lot of your time was spent on figuring out when a series would actually converge, and hopefully maybe determine the value of the series when it converges. Now, another thing you would have seen is the idea of a Taylor series. Now, a Taylor series is pretty much when we look at a function and we ask ourselves, well, this function is kind of messy, I don't know how to deal with it. Is there a way to express it as something a lot nicer, such as a polynomial? Polynomials are very nice. We can integrate them easily, we can differentiate them easily. They're continuous everywhere, they're differentiable everywhere. They're very nice things. And so we always try to wonder, is there a way to express functions in a more convenient form? And it turns out sometimes there are. If f is infinitely differentiable, not all functions are. I know that pretty much all the examples you've seen in Calculus 1 so far have been infinitely differentiable, but that's actually a very strange thing to occur. Here is what we can do. And we assume we can write f of x as an infinite polynomial, an infinite series of terms that looks like this. Now clearly if f is itself is a polynomial, there will be a finite list of such things, but what if f isn't a polynomial? Well, it turns out that we could actually do something like the following. We could say, well, f prime is going to be, well, a1 plus 2a
X2.
2a2 x plus 3a3 x cubed
X squared.
x squared plus dot dot. And we could look at something like the second derivative. Right? And we would get what? 2a2 plus 6a3 plus 6a3x plus dot dot. And we can look at things like the third derivative. And we would get 6a3 plus, what would the next guy be?
Wait, wouldn't you get A2 first?
Come again?
Wouldn't you get A2 plus?
A2 where?
From second derivative to
A2 is a
third.
constant.
The A's are constants,
Oh.
right? This is a polynomial. So X is a variable. The AI are constants. I'm writing it as a polynomial, so the A's are the constant terms. Now the next term here would of course be a to the fourth, x to the fourth, plus dot dot dot, which means once I take the first derivative, that's 4a4 x cubed, which means down here there will be 12a4 x squared, dot, dot, dot. And so here you would have 24 a to the fourth x plus dot, dot, dot. And then we can do something that we tried to solve for the a's. Now, how can we solve for the a's when there's an infinite list? Well, we start to evaluate the zeros. And now we consider
Is that a factorial?
what is f of 0, what is f prime of 0, what is f double prime of 0, etc. And you would realize that you would actually be able to get a list. F of 0 would be a 0, f prime of 0 would be a 1, f double prime at 0 would be 2a2, f triple prime at 0 would be
6A3.
6a3, f to the fourth prime at 0 would be
24A4. 24A4.
24a4, etc. And now we try to find a pattern for these numbers. Now, there's a point to this because we're going to be doing similar to this, but not exactly this crazy. Eventually, we'll be looking at similar things to this. Okay, so now this means that our A0 would be f of 0, our A1 would be f prime of 0, our A2 would be f double prime of 0 over 2, our A3 would be f triple prime of 0 over 6, our A4 would be fourth derivative evaluated at 0 over 24, and etc. And then we come up, well, what is there a pattern that happens here? And it turns out that there is. You'll notice that the denominators, 1, 1, 2, 6, 24, these guys can be written as factorials, right? So this guy is over a 0 factorial. This is the 0th derivative evaluated at 0 over the 0th factorial. This guy is the first derivative evaluated at 0 over 1 factorial. This guy is the second derivative evaluated at 0 over 2 factorial. This guy is the third derivative evaluated at 0 over 3 factorial. This guy is actually the fourth derivative evaluated at 0 over 4 factorial, etc. And we kind of come up with this pattern that the nth term is going to be the nth derivative evaluated at 0 over n factorial. And so this means that if I wanted to write f of x as a0 plus a1x plus a2x squared plus etc., I could actually write this as a sum of terms that will have this form, f to the n of 0 over n factorial times x to the n, where n starts from 0 to infinity. This is a special Taylor series. Called a Maclaurin series. However, in general, I didn't have to actually center it at 0. I could center it at something else. So I can imagine that this polynomial is shifted. We could shift this polynomial. So I could think of f of x as being centered at some other number. Let's say it's a constant plus a1 x minus x naught plus a2 x minus naught squared plus etc. And you get f of x equals f to the n evaluated at x naught, because me plugging in x naught would create the zeros, over n factorial times x minus x naught to the n. And so I would be able to express this function as a series in the event that I can find the derivative an infinite number of times. Now, not all functions will converge to their power series, and this is if we think of f to the n evaluated at x naught as over n factorial as just some number. It's just a function. It's a way to get a list of terms. Then this means I can think of my function as this guy. And this is called a power series, because it expresses f as a power function, as a polynomial. This is what we want to pretend. This is what we assume our y can be written as. Now, sometimes we know this guy will actually converge to a function in the sense that they're indistinguishable. I can use the series to represent that function in every possible way. That happens when you do something called Taylor's inequality and the remainder approaches zero. Doesn't always happen, but whenever it happens, it's really nice. Now, sometimes Fn converges, or let's put it the other way. The power series converges to F in the sense that they are interchangeable. You can write one in the other's place and no one's going to know the difference. Which is a very powerful thing. And in fact, there are some such functions that you should have memorized by heart. For example, we have
e to the x.
We know how to write e to the x as such a kind of function. We know how to write sine of x as such a kind of function. We know how to write cosine of x as such a kind of function. We know how to write 1 over 1 minus x as such a kind of function.
Square root.
Tangent.
These are the, we'll get to tangents. These are the ones that we actually know some nice formulas for them. E to the x was what?
X to the n over n factorial.
X to the n over n factorial. By the way, these are the Maclaurin series. So I can do that formula for e to the x, and I can ultimately derive that. For sine, x to the 2n plus 1 over 2n plus 1 factorial. Cosine
Positive.
is
2n over 2n.
x to the 2n over 2n factorial. This guy?
X to the
So it's x to the n. They also have domains where they work. So this one, these three here, works for all real x. No matter where you are on the real line, I can replace e to the x with this, I can replace sine x with that, I can replace cosine x with that. You're not going to know the difference anywhere on the real line. This one, though, it works
X is not
Acceptable.
strictly between -1 and +1. which means if you're outside of that range, I can no longer replace that function with a series.
Why is that?
It fails the convergence test. If you do the ratio test with that, you'll realize that it will only converge on, the radius of convergence is going to be of length 1. Whereas with these, the radius of convergence is of length infinity. Okay, what else do I want to tell you guys about?
Can the square root be written as a power?
Yes. Now, as I said, these can represent the functions in every context. So, for example, when the series converges, we can treat them as the function. So, for example, we can compose. So, for example, if I wanted to write e to the minus x squared, all I would have to do is go to that power series, and wherever I see x, I would plug in minus x squared. Right? I can literally just plug into the series just like I could plug into the function. Now this would be minus 1 to the n x to the 2n over n factorial, which means
It's cosine. No,
that's not cosine, there's no 2n.
cosine times n factorial.
So, which means e to the x, I can think of it as, what would I think of it as? If I plug in n equals 0, I would get 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus blah, blah, blah. I can think of the function e to the minus x squared as, now I can plug in 0 to here. So that would be 1 minus x squared over 2 factorial. 1 minus x squared plus x to the 4th over 2 factorial plus x to the 6th over 3 factorial plus etc.
Minus.
And we can do calculus with it. Thank the Lord. So, in the same way that I can do calculus, like I could differentiate e to the x, I would be able to differentiate that series. They are literally interchangeable. So this is called term-by-term differentiation.
Why is the third term in e to the negative x squared example not a negative x to the 6th?
It should be a negative, because this is an alternating sign. So it's plus, minus, plus, minus. So we can do something called term-by-term differentiation. So this means, for example, if I wanted to actually look at what the derivative of e to the x would look like, I can actually just differentiate that side. Derivative of 1 is 0, derivative of x is 1, plus this would be x, plus the 3 would come down, and I would get 3x squared over 3 factorial, which, by the way,
2 factorial?
simplifies the 2 factorial, plus the next one would be x to the 4th over 4 factorial. That's going to be 4x to the 4th over 4 factorial, which, by the way, that would cancel with the 4 factorial, makes that
4x cubed.
4x cubed, and you get that. And what do you notice?
It's the same.
It's the same thing, right? And I want you to also appreciate another way I could write this then is the following.
Oh, this is the thing at the beginning of that book, right?
What?
At the beginning of that book, the infamous.
Oh yeah, he wrote it as the series version. He doesn't write out the polynomial. That's too long. It's not elegant enough. He writes it as a series. He just moves sigmas around.
But it's
Okay.
You could get.
So another way that you can think about this is that I could think of this as differentiating the summation x to the n over n factorial, as n goes from 0 to infinity. This is the same as the sum this would be, you literally can do the power rule on this thing.
Oh.
By the way,
nx to the power of n minus 1.
do we remember when we can do this? When can we switch series with calculus operations?
Only if singularity.
We need absolute convergence. So the thing is, to actually prove that these series converge to these functions, you might remember in calculus 3 you proved it using the ratio test, which when it converges absolutely. You need absolute convergence. There's actually a theorem called the rearrangement theorem, which is very strange. Basically, it says if your series converges but it does not converge absolutely, you can change the answer by reordering the terms. So the order in which you add them can actually cause the series to add up to a different thing. And in fact, it's crazier. You can actually choose what number you want it to add up to and find an arrangement that adds up to that number. So if I have a series that converges and it converges conditionally, I can say, you know what? I want it to add up to pi. There's a way you can order the terms to get it to add up to pi. And I feel like I want it to add up to e squared over 3. There's a way you can order the terms to get it to add up to e squared over 3.
Can you show us?
Whenever you are, that's way beyond the scope of this class.
Wait, wouldn't that?
Whenever you have an absolutely convergent series though,
It only goes to one thing, right?
it will always converge to the same number, no matter how you reorder it. That is important because now, when you want to differentiate term by term, you don't have to worry about someone changing the order on you and it might change the answer, right? Because now, what are you differentiating? You don't know. It depends on what order you gave it to me in. However, if it's absolutely convergent, it doesn't matter. I can literally differentiate term by term at will, right? So this allows me to move calculus inside the series and actually operate on this. You will notice that what I would get in that case is going to be, yeah, so it's crazy, look it up. Look up rearrangement theorem. You probably won't understand the proof, but it's nice to understand the idea. After you take like real analysis or advanced calculus, you'll be able to read the proof and get it.
It feels like a thing where you can add, you can take one and subtract one
Yeah,
over and
you can
over
get a
again infinitely, and it either adds up to 0 or 1.
Or
and
half.
then parentheses in it.
Is that binary number?
That one, I know what you're talking about, but that one's kind of weird because that series doesn't converge in the first place, according to our definition. Anyway, I can do the power rule. So this would be n x to the n minus 1 over n factorial. This is going to be pretty much n x to the n minus 1 over n minus 1 factorial.
So,
And here, what you can do is, because if I started at 0, I would get a fraction, I can actually shift the terms. Now that's an important idea I want you to understand. We can shift the index.
we can't start it at 1, right? So we have to start at 2?
Come again?
We can't start at 1, right?
We can.
Because you get 1 minus 1 to 0 at the bottom.
0 factorial is 1.
Oh, right, it's factorial.
Yeah, I mean,
Yeah.
technically if you wanted to worry about shifting, which we're going to talk about, I don't want to throw too many things at you. We could have called this 1 here. Why? Because at n equals 0, it just wipes everything out, and so I'm adding 0. So I could have started that at 1. So now this, what you'll realize is that if I start this at 1, it literally gives me the original. Right? Because if I plug in n equals 1, it starts at the x equals 0. It starts at the 0 power over 0 factorial. I would literally repeat that series. But I can just rewrite it nicer. I can literally shift my n's to n plus 1. So I can go through and I can change all the n's in the series to n plus 1s. So wherever I see this n, I can change it to n plus 1. Over here, I see that n, I can change it to n plus 1. And over here, I can change that n to n plus 1. So what you're going to realize happens now I can add 1 to both sides, subtract 1 from both sides. And here I get x to the n over n factorial. So here you can see from the power series, you differentiate e to the x, you can get back e to the x. There's a way to actually get those series back. And this is an important idea, the fact that we can actually move calculus inside once we have absolute convergence, as well as we can shift terms to get it in a convenient form.
Is there a relationship between absolute convergence and the singular points that we were talking about earlier?
Oh yeah, that's a totally different ballgame. We'll get to that eventually.
Does this mean you can integrate e to the negative x squared?
Yes,
And it has a
I
solution?
was going to get to that.
Oh.
So here's one
Spoiler.
spoiler alert. So here's how series can be very useful. One of many ways. They're very useful. We can easily get answers we couldn't get before.
Why is easily in parentheses?
Because it is easy. Easy in the sense that doing it with a series is like you're doing it with a polynomial. Working with polynomials is easy compared to everything else, right? So, we can look at something like e to the minus x squared integrated. Without series, impossible, right? But with series, what I can do is I can think of this as the series of minus 1 to the n x to n over n factorial. I have absolute convergence, so I can switch the integral and the summation sign. Then I can just do the power rule. So this just becomes, I want to integrate, so I'm going to add 1 to the power and divide by the new power. And that is the integral of e to the minus x squared. Now, it is worth noting that we do not have the machinery to know what that actually adds up to, but we know it adds up to something. We know it converges. You can do the ratio test and know that, hey, that adds up to an answer. It's just that for the familiar functions that we know of, there's no way for us to write it in a way that we can understand in a way other than the series. Right? So if you look at all the basic building blocks of functions that we know, right, the 6 infinity stones of functions, right? Polynomials, radicals, rationals, trig functions, logarithms, exponentials, and all the combinations of those that we can do with arithmetic, combination, composition, multiplication, raising things to powers. We cannot express that series in any of those ways. So we just know there's an answer, but we can't write it down. And so this is what you might hear people say sometimes. Well, integral of e to the x squared, we do not have an answer in the elementary functions. That's what they mean. But we do have an answer in series. And what the series is good for is that we can now use the series to approximate the answer, which is great, right? There are theorems that will tell me, if I add up a certain number of terms, how close am I to the actual answer, right? And so a lot of those theorems you can even choose. You can say, okay, I want to know what the integral of e to the minus x squared is within 5 decimal place accuracy, and you can get it to work, right? You can choose your accuracy, and that's all you need to know, because you can never be infinitely accurate anyway, right? So that's good enough, and so we can approximate answers with the series.
What's the range for the integral?
For like a definite integral. And that's why I put answers in quotations. So the answers might not be something we can actually get our hands on, but we can get as close to it as we want without technically ever getting there. And this is why to bring it back full circle, it is going to be very useful with differential equations. There are going to be times when we're faced with a differential equation. There's no way I know how to find that answer in terms of functions that I know about. The variation of parameters is not going to work out for me. I don't know how to integrate this thing. I don't know how to deal with the differential equation I have. What you can then just pretend is that your solution looks like a power series. And that makes it a polynomial. I can do anything with a polynomial. And then I can just approximate the answer to that differential equation to within any degree of accuracy I want. So that's kind of the idea. And this, because of course I'm differentiating, I need to find like y prime, y double prime. This is very useful for ODEs. Let's talk about more important ideas in series. You can choose where to start them. That's going to be important. So, for example, if I have a series starting at n equals 0 to of an, I know that's a0 plus a1 plus a2 plus a3 plus a4 plus dot dot dot. But let's say I wanted to start at n equals 2 for whatever reason. You'll see a reason later. What I can do is I can just evaluate some of the terms and then start the series from some point in the middle. So I can just write this as a0 plus a1 plus, now I can start adding up the terms from n equals 2. Right? So I can actually just evaluate a few terms to get it off the series and then start it at some other arbitrary point. That's going to be useful. That is useful because we're going to want to be able to combine series, add them together, and multiply things inside them and combine them. And in order to combine series, I need them to start at the same point. Right, you need your series to be in line with where they're starting. So, for example, if I have a series of an starting from 0, I can add it to another series of bn, and I can just bring those guys all inside one big series expression. But in order to do that, this must be the same. So, if for some reason these guys don't match up, I can use that trick that I just showed you over there. So let's say this guy's at 2, that guy's at 0. What I can do is I can evaluate a couple terms here to get him to start at 2, and then combine the series starting at 2 with the extra terms outside here. Right? That's something that we should know we're able to do. So that will allow us to add 2 series together.
Can you ever make one go down from 2 to 0?
Very rarely, but usually you'd have to like add and subtract something or add 0 in a convenient way.
How would you go from 2 to 0? Do you integrate?
So technically you could. Didn't we do that earlier? I don't remember that I actually did it earlier. Okay. Shift, shift. So, I mean, if we cut the suspense. Let's actually do a very simple example so you can kind of see what I'm talking about. Let's just jump into it. Y double prime plus y equals 0. We know what that solution is, right? Sin x and cosine x, right? How would we actually solve this using a series? Find a series solution centered at x naught equals 0. So basically, this means we're going to assume our y is some series a n x minus x naught to the n goes from 0 to infinity. If my x naught is 0, this just looks like a n x to the n. Now, if that's my function, how do I know it's going to solve that differential equation? You plug it in, right? Just like always, we're going to plug it in and we need to solve for the coefficients that makes it work. So, this means I need to be able to find y prime.
Wait, do we have to check if it converges absolutely?
No, we're going to assume it converges. You can check it converges absolutely afterwards, which once you find what the an is, you'll need to know the an before. Now if I differentiate that, I can differentiate term by term as n a n x to the n minus 1. Now I can start at 1 because if I start at 0, it's not going to change anything. Notice that I can take the next derivative and I can start that at 2. This is n times n minus 1, a n x to the n minus 2. I can start that at 2 because if I plug in 0 or 1, it's going to cancel. It's going to be me adding zeros. And then what I can do is I can actually plug it into that position. So, this means if I take the series n times n minus 1, a n x to the n, those series should add up to 0. Now here's how we are going to start figuring out what the y has to be. First thing I'm going to do is get the powers the same.
So what is n equal to? Why is n equal
Because if it's 0 or 1, it gives me 0, so it doesn't make any difference.
to?
If I were to start at 0, n equals 0, it would just add 0 2 times and then start the actual series. So I'm going to want to be able to combine these series, factor out common terms, and so on. So I want these guys, the powers of x, to be the same so I can combine like terms. How can I get the powers to be the same? Well, I can shift the index. I am going to shift all n's to n plus 2's. So that means this series will now start at 0. This will be n plus 2. This will be n plus 1. This will be a n plus 2. This will be x to the n. Now, I have the powers are the same. And, coincidentally, I also now have the indices that are the same. Now, technically, that would be the next step.
Wait,
So
Professor?
this was step 1. So once you plug it into the series, you're going to start to maneuver it to be something convenient.
Professor?
Yes.
Didn't you say the indices has to be the same to combine them?
Yes.
Which
Which it now is.
Oh. But to do that, you have to make the powers the same first.
Huh?
To combine them, do you have to to see if the indices are the same or the power are the same? Which one do you do first?
So I get the powers to be the same because I want to be able to combine like terms. In order to combine the series, I need the indexes to be the same, the indices to be the same. That's already happened. So now what's going to happen? Well,
You need a series for 0?
we don't need the series to start at 0, but
No, I mean, don't we need a series to represent 0?
Yeah.
no, not necessarily. I mean, technically you can think of it that way, but
0 plus 0 plus 0.
so here, now I can combine the whole series. Now, this is step 3. Combine all series. once you get all of the powers the same and all the indexes to be the same, you're going to combine all the series. So now I can get one big series, n equals 0 to infinity, of n plus 2, n plus 1, a n plus 2, plus a n, x to the n equals 0. So now, yes, if you can think of 0 as the series at this point, you can kind of think of this as, oh, this is just 0 plus 0x plus 0x squared plus, right?
Yeah.
So what you notice here is all the coefficients are 0. So you equate coefficients of like terms, basically you get that this here must be 0. Right? So now what? So that means n plus 2 times n plus 1, a n plus 2 plus a n equals 0. Step 4. Solve for the highest index. Here I have n plus 2 and n are the indices. N plus 2 is the bigger one. So I'm going to solve for a n plus 2. You'll notice this is minus a n over
N squared.
n plus 2, well, n plus 1 n plus a. This guy here is called a recurrence relation. AKA recursive formula, any such thing. Notice what that does is it tells us how to compute coefficients 2 steps ahead if I know coefficients 2 steps behind.
I got a question on the right half of that.
Yeah.
How'd you go from the,
Subtract an, divide both sides by a coefficient.
no,
of
the bottom, right here
Oh,
says,
here?
yeah, n equals 2, and then the one below it you have to the right. Yeah, from the top to the bottom, that's.
Oh, I did a shift. I literally went everywhere I saw n and wrote n plus 2's.
Okay. And then that.
Why? I did that because I want the n minus 2 to become an n. So I do n plus 2, it will kill the minus 2,
Yeah,
and create an n.
okay.
So I can shift everyone 2 spaces over. So this one gets shifted to 0, this gets shifted to n plus 2, that gets shifted to n plus 1, this an gets shifted to an plus 2, and the n minus 2 gets shifted to n. Now, here's something I want you to notice. We're almost at the end, and this is a very short problem, by the way, for this thing. So, A0 and A1, in this case, these guys are usually going to be given, or you just leave them arbitrary. Why? Because they're actually going to be your initial conditions. This guy is going to be the y of 0. This guy is going to be the y prime of 0. Actually, write out the power series and you'll see y. Right? See y and y prime of 0. These guys will be your initial conditions. So here, I'm just going to leave A0 and A1 as these conditions, which I'm going to plug in. And what I'm going to do now is solve for all other coefficients in terms of A0 and A1. So, how would I find A2?
Wasn't n equal 0 for A2?
Right, I go to the recurrence relation. This tells me how to, if I know the previous 2 guys, I can find the next guy. So I can get A2 by plugging in n equals 0. So if I plug in n equals 0 in my recurrence relation, I will get minus A0 over 1 times 2. What about A3? Well, this is when I plug in n equals 1. And I will get minus A1 over 2 times 3.
That's factorial.
It is a factorial. Well, hold on. We're going to keep going until we start to see a clear pattern. N equals 2 would give me A4. That will give me minus A2 over 3 times 4. Now remember, I want everyone written in terms of these because those are going to be my initial conditions. So the A2, I'm going to actually replace with that. So if I take this and plug it here, I'm going to end up with positive A0 over 1 times 2 times 3 times 4. My A5, this is when I plug in n equals 3. That's going to be minus A3 over 4 times 5. I don't want A3, I want everyone in terms of A0 and A1. So I go back to A3. It's this guy I'm going to plug into here. Then I will get positive A1 over 2 times 3 times 4 times 5. And I assume you guys are starting to see the pattern here. So this is minus A0 over 2 factorial. This guy is minus A1 over 3 factorial. This guy's A0 over 4 factorial. This guy's A1 over 5 factorial, etc.
What would the
So-
next term be? Would it be negative A0 or?
Negative A0 over 6 factorial.
Oh, so it's double negative, double positive.
Yeah. So, finally, we actually now know how to write the answer. Why? Now, this means, so we see a pattern here, which is what we want. Once you see the pattern, you stop. You're either going to stop when I tell you to stop, oh, find the first 4 terms, or you stop when you see a pattern and you can actually take advantage of it. Remember what our original assumption was. Y is just this statement, right? But what is that? Well, that's A0 plus A1x plus A2x squared plus A3x cubed plus A4x4 plus dot dot dot, right? A0 is A0, A1 is A1. A2 is minus A0 over 2 factorial. A3 is minus A, so this is x squared. A3 is minus A1 over 3 factorial, x cubed. A4 is plus A0 over 4 factorial, x to the 4th. A5, you'll realize, is plus A1 over 5 factorial, x to the 5th. And it will continue. Now here's something cool. And the pattern continues, right? So the next one is going to be minus A0 over 6 factorial times x to the 6th, then minus A1 over 7 factorial, x to the 7th, etc. What I can do now is I can group the A0s and the A1s. Right? That's kind of like my C1 and C2 of these functions. What are the guys in front of the A0? What would I have over here?
1 minus.
1.
Oh, that's cosine.
That's cosine.
Oh, wow.
What? Hold on. Hold the phone. I know that guy. That's friggin' cosine. What's going to happen over here?
Sine. I sine.
Spoiler alert. You factor out the A1, you're going to have x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus. That's sine. I just figured out the solution to the differential. differential equation. Now, in this situation, the heavens have smiled upon us. They have given us a series where, hey, I actually recognize this answer. That never works.
Your hands are white.
What?
Your hands are white.
Oh, we're gonna like have a still photo for a while. We're gonna like make a meme out of it. Right. This doesn't always happen, right? Like, oh yeah, I recognize that series. A lot of times that series is like, I don't know what it is, right? It's just this weird function that I couldn't have found any other way. But the series way allows us to get to an answer. It's tedious working through it, but at the end of the day, you are working with polynomials, and that's kind of easier. So if you have no other method to go with, this is a viable option.
So if we don't see something that we can change that series into that's mutable, we leave it as a series.
Yep.
And the answer.
And I want you to appreciate that now we can solve all sorts of crazy things. So for example, now if I had y prime plus say 3x to the 7th y prime minus xy equals 0, we don't have a way of solving that.
What do you do now?
The series we do now. Right? So as a series multiplying the x, you just bump up the power by 7. Right? You go through this, you shift all the powers to be the same, and then you compute the coefficients, you can get a series answer to this. I won't say easy, it's straightforward. It'll take a while, but I can find an answer to that. And maybe it might be a function that I recognize elsewhere, but sometimes I have it as a series, and that's good enough. I can approximate it. Anyway, we'll pick up next time with that. We'll stop there.
Is it gonna do it next time?
Huh?
Is it gonna do it next time?
The next quiz I think is going to be after Thanksgiving.
Sounds good to me. Thanks.
Kind of like a half a class behind. I want to catch up. It's a test case.